which we discussed last week. What was this about? This was about this equivalence of the geometric description of Hurwitz numbers and the combinatorial, right? And after that, we will formulate another way of how to describe topological recursion. So there is another approach, which is called the approach via the loop equations. So we'll formulate those loop equations, and from there we will. Let me give you a plan. Our plan for this class today, and then a couple of weeks further, will be to. So we'll start discussing this. Up to now, we were able to check by hand some small cases, some simple examples where we can by hand see that topological recursion works for various types of Hurwitz numbers. But we want to prove it, right? And there are actually various ways to prove topological recursion for Hurwitz numbers, but we will be discussing one of them. Why choosing this particular way to prove this? Because historically, so how do people prove topological recursion for Hurwitz numbers? Historically, it happened like that. The first proof of topological recursion for Hurwitz numbers was by a rather complicated formula, which is called the ELSV formula. So it related Hurwitz numbers to some quite complicated concepts in algebraic geometry. So in algebraic geometry, you have so-called intersection numbers on the moduli space of algebraic curves. Maybe someone heard about them. They're related to Gromov-Witten invariance. And there was this very famous formula by Ekidal, Landau, Shapiro, and Weinstein, which related Hurwitz numbers to this intersection. And people, so the first proof how to get topological recursion was by using this complicated formula in order to obtain the statement regarding topological recursion. So this was the first proof. Then there appeared purely combinatorial proofs of that. So I mean, we do not, if we look at Hurwitz numbers, the topological recursion is more or less a combinatorial statement, right? It's a formal, some formal expression, expansion. You take the expansion and you compare on both sides. So it shouldn't require some complicated algebraic geometry with homology classes and so on to prove this statement, right? It would seem that it shouldn't require that. And indeed, it turned out that it was possible to do this, to prove it directly in a combinatorial way, starting from the cut and join equation. We talked a bit about the cut and join equation, right? You remember that? So there is a way to prove using the cut and join equation for Hurwitz numbers to prove topological recursion. And this is fine. We can prove for simple Hurwitz numbers, for instance, this using the cut and join equation. But it's not optimal in the sense that if you want to consider this in general, not just for simple Hurwitz numbers, but also for monotone Hurwitz numbers, also for various types of generalizations for that, this approach using the cut and join equation is not very good, because you need for each particular case, for every new case, like if you want to prove monotone, orbifold Hurwitz numbers, R-spin Hurwitz numbers, and so on, various types of Hurwitz numbers, which we will also discuss later in what follows. for each of those cases, you need to start in U. So you need to make a very complicated combinatorial reasoning and start basically from scratch in every such case. And it's very complicated, so there appeared several papers for various cases, each of them for on like 20 or 30 pages. People proved how this worked for specific situations. But you have to do this one by one, all those cases one by one, and basically every time you have to do it from scratch. Not precisely from scratch, but you cannot do this in this approach for all the cases together. So that's why we will not actually discuss this approach, and we will discuss another approach, which does not use the cut and join equation, but instead it uses the representation of Fourier numbers in terms of the so-called Kp tau function. So somebody maybe heard about what's called the Kp hierarchy. It's an integrable hierarchy, Cousins-Dashvili integrable hierarchy, and it's a system of infinitely many differential equations, and there are solutions for those systems, and there are many classes of solutions, and it turns out that a particular class of solutions of this integrable hierarchy is related to Fourier-type numbers. And basically all of the Fourier-type numbers I mentioned, the ones which we encountered, and many generalizations, they fall into this class. And after you represent them in terms of this, what's called the tau function of Kp hierarchy, there is a way to prove topological recursion in general, basically for many cases simultaneously, including the simple Fourier numbers, the monotone, and so on. So you prove it once and for a very wide family of Fourier-type numbers. So this is what we are going to discuss. We are going to, we've seen by hand that this works for some particular cases, and regarding the proof, we are going to to prove it in general because it's simpler. To prove that the topological recursion works in this very general situation. That's what we're going to do. And in order to do that, we need to reformulate the topological recursion. So our original formulation is how it appeared. In terms of this recursive relation involving residues and so on. This is the original formulation of the topological recursion. But for our purposes of proving it for this general family of Fourier-type problems, we need to reformulate it in terms of what's called loop equations. So, am I making sense? Is it clear what is our plan? Any questions? Was it at least somewhat clear what I'm meaning, or it's just some words which do not make sense? Okay,
so let's move on.
Okay, so plan is clear, right? I'm explaining this in order to explain why do we need this reformulation. You might ask, we haven't even managed to prove the original version of recursion for any sort of problem. Why do we reformulate it at this point? What is the reason for that? So that's why I explained our plan. Because this is the actually a simpler way to prove it for many problems together. So like I said, you can use the original formulation and relate it to cut and join, but it's quite complicated and it works only on case by case. Okay? That's why we will go in a different, we will use a different approach. So now let's finish our discussion regarding this. Do you remember where we stopped here? So recall that we have our, so we have this geometric formula, right? So we want to, probably it's not clear to online participants where I'm pointing at, right?
No, it's better if you like maybe circle something and then
okay. So we have
undo the
I can just maybe I can even. So we have this. We have this formula. So where we sum over all equivalence classes of coverings with this weight, right? We take the sum for each covering. We assign to this weight 1 over the number of automorphisms. Last time we discussed what was this guy, right? And so we sum our overall equivalence classes, and our other definition was, where was it? This one, right? Yes. So our other definition was counting the m tuples of transpositions, dividing it by 1 over size of a mu factorial times 1 over m factorial. Actually, yeah. So we want to relate those two things, right? That's where we stopped last time. We want to relate those expressions in the yellow circles, right? Basically, recall that we added this 1 over m factorial in order for the generating function to look simpler, right? In fact, we will have to, if we want to equate this formula with that one, we'll have to add 1 over m factorial as well here. So see, here we have this combinatorial factor, which we'll have to include this 1 over m factorial. But let's see how it works. So we can, let's first try to see this on some example. Recall that we have this example here, where, yeah, where was it? Yes. So this example, this covering, z to z squared, right? This function, this covering. What does it correspond to in terms of, so how many ramification points are there? Let's go back to this example. Do you see it here? So we have the
0 and things.
Yes, so there are 2 ramification points in this example. The point 0 and the point infinity, right? And what are the ramification profiles there? Yeah, well, I mean, I meant that what are the, so how does this look in this similar way like here? So in this example, we have so CP1, infinity, 0, and we have only two sheets, right? And over infinity, we'll have a simple branching point, right? And over 0 as well, a simple branching point. And over some general point, it's just like this, right? So what does it correspond to? What does it correspond to in terms of G and mu?
G is 0 and mu is a transposition.
It's 0, but I mean it's not. Mu is a collection of numbers, right?
2.
It's 0, 2. Right? Okay. Let's check that our Riemann-Furri's formula produces what we actually want here, right? So we want, what is M? M was, so who remembers, what is the Riemann-Furri's formula? What? What should I write here?
2g minus 2.
2g minus 2. 2g minus 2 plus size of mu plus length of mu. Let me write it as L of mu. It's clear what is this L of mu? It's length of mu, which we usually call M, right? And in this case, it's what? 0 minus 2 plus size of mu is the sum over all mu i's, it's 2, and plus length of mu, which is 1, and we see that it's 1 here, and this is precisely what we expected, right? I mean, no contradiction in science here, right? So we expected that we only have one simple branching point, and that's what we got. But then, let's see what does our definition, which one? Yes. What does this definition give us for this particular example?
I'm afraid that in such a simple case, we will not see the meaning of all this.
No, I think in at least some we will see something.
All factorials will disappear, but okay.
Not all of them.
But almost all.
Well, let's see. I mean, no, we will see. Actually, we will actually see some correspondence here. So let's look at this, at this definition. What does it give us in this example? So where m equals 1, g equals 0, mu equals 2.
Gives us 1 or 2.
So what is the, first of all, what do we see here in the brackets?
Number of ways to decompose a transposition into a transposition.
What is this number?
1.
In this case, yes, we only have S2, right? So the since we group over 2 elements, there is exactly one transposition there, and there is exactly one way to represent this transposition as a product of one transposition, right? And we have this factor, this combinatorial factor, 1 over m factorial, 1 over size of mu factorial. This does not play a role here, but this guy does. So we get, so in this example, it's 1. And let's look at the other definition. At this one. So how many equivalence classes of coverings are there? Just one. Why? Is it clear? I mean, we are looking at this sort of covering, right? So we fix our points, infinity and 0. And you remember that two coverings are equivalent if, in this case, I mean, above and below we have CP1s, right? So CP1 here and CP1 upstairs. So CP1. And we have two maps from CP1 to CP1, and they are equivalent if there is an automorphism, there is a homomorphism from CP1 to itself, such that the triangular diagram commutes, right? So let me write it again. So we have like our sigma, we have one covering F, we have some other covering F tilde, and they're equivalent if there is a homomorphism from sigma to sigma. How do you call it? Whatever. I mean, let's say it's capital. So that this diagram commutes, right? In particular, this can hold only if all the critical values are the same, right? For both of those coverings. In this case, 0 and infinity. So how many equivalence classes are there? You're saying that only one, but why? I mean, we have a representative of this equivalence class. It's this guy, right? We have an explicit formula for this function f from CP1 to CP1, this one. And we are interested in looking at all coverings such that they have only two critical values, 0 and infinity, and the ramification profile is like that, right? And we are saying that they are equivalent if there is such a map, capital F, such that this commutes. So why does any covering which has this profile, why is it equivalent to our given representative?
I know how to put it by reduction to previous computation because a covering is determined by its monotomy.
No, I mean we have to discuss this as well, right? So you're right, but we haven't yet discussed this in detail. Why is the covering determined by its monodromy and how does it work precisely? But for this example, can we see it directly?
We can say that this map sends 0 to 0, so at least it's a polynomial, doesn't have z to the power -1 and negative part. And it is of degree 2, so it's polynomial.
So wait. Why is it polynomial? I mean, we from the start we said that it was just some.
It's a rational function.
Well, I mean, in the definition, we only said that we were looking at some continuous functions.
Maybe we look at the standard complex structure on CP1 and we induce the complex structure on the covering space, and then we probably have to use uniformization to say that this, the covering space, which is a sphere, is also CP1.
Okay, and so what?
Well, and then we have a homomorphic map between from CP1 to CP1. And you know its ramification. So, as Lenny said.
But how do you go there from if we start with just any continuous map from sigma to 1? What can I say in that case?
think it will not be just continuous. So we induced by f and f tilde, we induced complex structures on sigma and sigma prime. And so I think it must follow that f is holomorphic.
In the induced complex structure.
Yes.
Yes. But I don't see why, but it's true. If this diagram is
I'm not sure what are you asking. So
I'm asking to directly see in this example. So we have this simplest case.
okay, so maybe you can explain, yeah, how.
No, I mean, what was our definition? What was our definition of coverings and equivalence classes? What was our original definition? What did we require of this set?
I mean, we are like, I'm afraid that we will stay in this basis of topology forever. So maybe like, maybe you can explain all this stuff and we go further.
I think, I mean, it's useful to, in this example, to see this, to think about this directly.
В этой формуле требуется повысить комбинаторные факты.
Мы как раз хотим это понять. Мы хотим понять это. Okay, so
we want to find such triangle where, for example, sigma prime is CP1.
in our case, yes, sigma. They're both sigma.
And f is just homeomorphism, right? F is homeomorphism. What?
So what was our definition of a covering? Let's recall. So it was just, what was a covering? Covering was a map from sigma to CP1. So it had to be continuous, right? And it had to, our requirement was that for every point apart from a finite number of critical values, for every point downstairs, the pre-image of a small disk around this point was just a disjoint union of disks, where the number of those disks is fixed for all regular points, and we have a finite number of ramification points, where at ramification points we can have something else. But still, it only can look, we can have smaller number of images for ramification points, but in the vicinity of critical points upstairs of each of those critical points, each of the pre-images of critical values, locally this looks like, this should always look like z to some power p, z to some power mu I, right? Yes.
I still believe that we can also change to homomorphic category. I mean, if we take only equivalence classes where f and f tilde and big F are all homomorphic maps, and the capital F is big homomorphic, we get the same number of equivalence.
Why? Why is it the same?
Well, I said because if we have a continuous map, ramified covering from some topological surface to CP1, we can induce.
Yes, you're actually right. So you can, if you have this a continuous map under such requirements, which we pose on our coverings, right? So if it looked like the way I described just now, right? Then you can, from there, indeed induce a complex structure upstairs on your sigma. And in this complex structure, it will be actually a meromorphic map. Right? This ERF will be a meromorphic map. Yes.
So in each class of covering, we have found a homomorphic covering by eliminate surface. And also have to say that if we had such triangle in the topological category, if we endow sigma and sigma prime with complex structure, then M becomes a homomorphism.
Okay.
So now
what can we say about our example?
So I think logic in my argument was wrong. We don't have such F leak, we want to construct it. Right?
Yes. We want to construct it in the sense that suppose we have some other covering with those properties, with the ramification profile being the same, and we want to show that there exists such right? I mean, that's precisely saying that you have any two such coverings are equivalent to each other, right? So that there is only one equivalence class.
Maybe we should throw out a ramification point and consider the universal covering and look at triangle.
You mean you throw out one of the ramification points from CP1? All of them, okay. And so what? So this will be a punctured complex plane. If you do that.
I need to think about this argument.
Let's think for a moment. So we want to see in our simplest example, right? So where the profile is like this. Why is there only one equivalence class? Is it clear? Is the question clear? So again, what we start with, we say that suppose there are two coverings with the same profiles. They are ramified only above 0 and infinity, and the ramifications are simple, and you have only two sheets for those two coverings. So why are they equivalent then?
If we reduce complex structure
Yes.
tests, then we get an isomorphism with CP1. A selected one.
Yes.
And if there are two, then we get two isomorphisms.
Yeah, and we also can choose our coordinate upstairs, for instance, such that this point will be 0 as well, right?
So as a test, we take 3 points downstairs, 0, 1 each regular point, and infinity. And we take the preimage of 0, infinity, and 1 of the preimages of 1.
and introduce our coordinate on CP1 exactly in such a way that those 3 points are, this uniquely fixes your choice of global coordinate on CP1, right? If you take any 3 points and say that they are going to be 0, 1, and infinity, right?
And we also see that this way we get one automorphism because we could choose any of 2 images of 1 to be 1 upstairs.
Yes. And I mean, actually, we're almost there because once we are Misha said, once we are in this complex situation, right? If you say that upstairs you have 0, this point is 0, then we say that locally this map should look like z to z squared, right? But then what does it look globally? If it's locally z to z squared, but also we, for instance, we see that at infinity we have the same thing, right? What can I say then in general of how this looks in those coordinates? And if you think about it, you'll see that actually this requirement says that it will look precisely the same. Globally, you will have to have a z map to z squared. So this map, once you choose the coordinates upstairs in the way we described, it must look as z to z squared, and that's it.
Может быть, ты можешь еще по-русски повторить теперь все от начала до конца?
Хорошо, значит, еще раз. Мы хотели на примере, когда у нас вот желтым, как здесь написано, такой есть профиль длины, случай, когда G...
Не-не, вроде бы условия понятно, решение.
Значит, решение. Мы говорим, что рассмотрим такую вот сверху на этой сфере, рассмотрим такую комплексную структуру, значит, ну, поскольку это сфера, то там достаточно одной карты, правильно? Значит, такую комплексную структуру, которая индуцирована нашим отображением, причем выберем, значит, вот глобальную координату таким образом, чтобы сверху 0 был прообразом нуля, значит, бесконечность была прообразом бесконечности, а единица была, вот, выберем один из 2 прообразов единицы. Да? И утверждается, что после этого обязательно это отображение в такой координате обязано выглядеть как, иметь формулу z переходит z квадрат. Ну вот, значит, надо подумать, какие у нас ограничения есть. Да? Значит, мы говорим, что в локальной координате около нуля, вот это, мы выбрали прообразом нуля 0. В локальной координате мы знаем, что в какой-то локальной координате она выглядит как z переходит z квадрат. Правильно? Почему это верно про глобальные координаты? Но у нас есть условия на остальных точках. Что мы про них знаем? Мы знаем, что, в частности, единица переходит тоже в единицу, да? Это мы так выбрали координаты. И бесконечность переходит в бесконечность.
Подожди, ты только что сказал, что единица либо в единицу, либо в минус. А, что единица переходит в единицу. Хорошо, да.
Переходит в единицу. Единица сверху переходит в единицу снизу. Ну, вот если вы запишете эти условия, они вам однозначно определят, что это и есть вот это локальных координатов, которые переходят в квадрат, если добавить условия на...
Ну, сейчас, ты все-таки тут пользуешься тем, что это рациональная функция.
Да?
Ты все-таки пользуешься тем, что это изначально рациональная функция?
Нет, я не пользуюсь. Я сказал, что это была какая угодно функция, а потом я ввел сверху...
А почему тогда условие, что 0 в 0, 1 в 1 тебе как-то ограничивает?
Я так выбрал глобальную координату сверху. Я сказал, что у меня комплексная структура индуцирована взятием прообраза относительно...
Да, хорошо. Почему, если ты фиксируешь, куда переходит 0, куда переходит 1, ты уже знаешь, что это z квадрат везде?
Потому что у меня есть... Я знаю, что это голоморфное отображение.
Угу.
Должно быть аналитическое.
Угу.
Причем локально оно выглядит как z квадрат, и единица переходит в единицу, а бесконечность — бесконечность. Из этого следует, что оно глобально выглядит как z квадрат.
Ну, потому что это рациональная функция, и у нее бесконечный переход в бесконечный.
Ну, собственно, комплексное-аналитичное отображение — это как раз и следует, что это рациональная функция. Правильно? Мероморфные функции cp1, cp1 — это только рациональные функции.
Ну вот, может быть, да, можно было так сразу сказать, и тогда немножко быстрее все. Да. Ну, просто мы начали с того, что... Да, ну хорошо.
Окей. Any questions at this
Не,
point?
сейчас, стоп. Ну, это пока понятно стало, что это... ну хорошо. И ты хочешь сказать, что оно такое единственное?
There is only one equivalence class.
Ну, хорошо.
And as Misha mentioned, we also, in the process, we've seen that there is one automorphism, right? For this, for a covering belonging to this equivalence class, there is one automorphism, which corresponds to choosing. You could choose either of the two reimages of one to be one upstairs. This corresponds to automorphism. I mean, actually, we don't even have to think about that in those terms. We can go back to our particular representative, z to z squared, and there we see our automorphism, like we discussed last week. We see it directly. Z maps to minus z. This is clearly an automorphism. Which means that in this here in this definition, in this sum we only have one term, and this term is 1/2, right? And in this here in this yellow circle, we also we have this. The set contains only one element, and we get 1/2 from this factor. And in fact, they coincide. So for this example, we see that this 1 over automorphism over the number of automorphisms, this corresponded to here 1 over size of mu factorial over here. So this is already a non-trivial for instance, actually, right? It's not that 1 is equal to 1. We get two factors of different sort producing the same answer which we want in that. So now we have to, what remains is to extend this logic to the general case. So like it was mentioned, so how does, in this bottommost picture here, we, last week we discussed how we, what was the relation between the covering and the combinatorial picture, right? So it was clear how to, if we start from some covering, then we can draw all those loops, and from there we obtain and we choose some way to number to order those sheets above our regular point, right? We take one possible choice of labeling those sheets above our regular point, and then after making this choice, you get your, if you have a covering, you end up with the some product of transpositions which give you a permutation, which is a permutation of your given cyclic type mu, right? Do you remember this? So is it clear what I'm saying? You remember this, right? So if we last time we discussed that when we go around one point of simple ramification point, then this corresponds to a transposition on the sheets, right? And when we go around infinity, where the ramification is not simple but rather is described by this profile, this corresponds to a permutation of the respective cyclic type, right? But now we want to compare actually the numbers, right? So you get, you have to, in our two definitions, we have to, in the combinatorial one, you take all possible ways of representing the permutation of a given cyclic type as a product of transpositions, and then divide by cyclic mu factorial and our additional factor of 1 over m factorial. And in this geometric picture, we take all classes of equivalence of coverings and take them with their weights, which are 1 over the number of automorphisms, right? So how do we relate those? It should be somewhat clear from our example, which we discussed just now. So how is it, what happens? What does the factor 1 over size of mu factorial correspond to? It corresponds to
choice of labeling the pre-images.
Precisely, yes. So we have our regular point Q, and there are precisely size of mu factorial ways to choose the labeling of our pre-images over this regular point. Okay.
How many vectors of pre?
No, I mean there are for over your regular point, you have how many pre-images of the regular point do you have? You have size of mu equals, I mean, we also call it d. D pre-images, or size of mu pre-images, which is the number of sheets, right, in your covering. And of course, the number of ways to label them from 1 to d is d factorial, right?
Yes.
So d factorial equals size of mu factorial ways to label
Geometric picture, the sheets are unlabeled.
Yes, in the geometric picture, of course, they are unlabeled. How would they be labeled?
Not all the labelings are equivalent, right?
Sorry?
Not all the labelings are equivalent.
So this is precisely what you're saying is precisely related to this factor 1 over automorphism. So we will let's look back at our picture, right? In our picture, in our example, in our simplest example, we had actually 2 ways of labeling the sheets, right? And they were equivalent. They were related by an automorphism, right? So in fact, this corresponded to the fact that 1 over the number of automorphisms in that case, it was equal to 1 over d factorial, the combinatorial side, and we got the same answer. So, but in general, you're right. So what happens? The number of ways to label the reimages of Q. Regular point. But now let's look at this at the general picture. In the general picture, we can have some automorphisms, right? And each of those automorphisms, it somehow permutes the sheets of the regular point, right? Like we've seen in our example. In our example, the automorphism it precisely interchanged our two ways of labeling, right? So each of the automorphisms it will correspond to some permutation of the label, right? But not every permutation corresponds to some automorphism. This we discussed last week, right? So what can we say?
Different ways to label is the factorial or modular automorphism.
Yes, you can. What can you actually count? You can count. So you can say that some number of ways to label are equivalent if they are related by automorphisms, right? And then if you factor by those things, you get actually different ways to label, right? And now we want to compare what we're counting on both sides. On one side, we're counting these collections of transpositions, which give you the permutation of your given cyclic type. And on the other side, we count the equivalence classes of coverings. And so how those two numbers how do they compare, those two numbers? Like I said, if we start with covering, we get our tuple of transpositions from there once we choose the labeling of the sheets over the regular point, right? But what is the correspondence? So I mean, how many to one is this correspondence? If you look all what we're saying is that take a covering, take a way to label the pre-images, you get a collection of transpositions.
So to add covering with an equivalence class of covering by choosing different labels, we associate unifactorial or out there.
Yes, so that's precisely what we obtain as a result of our whole discussion, right? So my point is that precisely if we take in this way, so we consider a covering with additional structure, namely the way to label the pre-images of Q, and to that we uniquely assign now a collection of transpositions. So how many cases are there? Precisely like that. So this corresponds to so every equivalence class of coverings as a result of our discussion, it corresponds to the if you take all possible choices of labelings, it corresponds to the mu factorial divided by number of automorphisms number of automorphisms. So this number, it is precisely what you get over there on the combinatorial side.
А ты можешь, может быть, какую-то табличку нарисовать? Потому что я лично запутался. Учли все автоморфизмы или не учли и факториалы?
Okay, let me write it precisely. So F covering, and then a way to label, and L labeling of preimages of Q. It maps to tau 1 and so on tau n. Is it clear? So if we pick a covering and a labeling, it uniquely produces for you a collection of M transpositions in the way we discussed, right? And the claim is that
not only in transpositions, but with numbering for cycles, right?
With numbering, no.
No?
Why? Why do we have numbering of cycles?
Because we have some definition.
Yes. Well,
No, but this is, like I said, so this is...
Это не из определения, это из конструкции.
You're right that in this definition we wanted to have numbering of cycles.
Да, но внизу написано конструкция, как по накрытию, как получается набор перестановок, и по конструкции он получается пока с ненумерованными циклами.
кажется, как раз с нумерованными.
Почему?
Если мы слои занумеровали.
Слои занумеровали, да.
Никак не
Но это не дает вам порядок.
Это же порядок циклов, это другое.
Просто вам, если слои занумеровали, у вас получается просто известна какая перестановка в произведении. То есть над бесконечностью, это соответствует какой-то перестановке.
Просто слои должны быть пронумерованы, чтобы получились перестановки какие-то. Чтобы было множество индексов, которые мы переставляем.
Просто на самом деле вот этот множитель, его придется там добавить руками. Эту формулу тоже. Вот. То есть на самом деле мы получим вот это определение из единиц на автоморфизме. Вот этот множитель, он будет руками добавлен. И m факториал тоже руками. То есть вот само по себе сумма единицы на число автоморфизма дает вам только вот эту часть. Единицы на μ факториал и на количество с ненумерованными циклами. А нумерованный цикл это без руками.
Давайте допишем внизу это соответствие со всеми факториалами все-таки.
Okay, so we have again a covering and a labeling. It produces your transpositions, but then what we're saying is that for a given covering with all possible labelings, so let's look at so this map, let's call it, I don't know, phi, and consider what is phi of for a fixed f fixed, and for all possible labels. So consider the image of for some covering, fixed covering with all possible labels. This will give you some collection of transpositions, and the point is that the number of those guys is precisely mu factorial over the automorphisms of F. So this is the claim, right?
А ты можешь еще раз по-русски повторить?
Вот еще раз, мы каждый накрытию и способу пронумеровать слои мы сопоставляем набор транспозиций. Да? То есть вот у нас, например, в том примере, который мы рассматривали простейший, там у нас было накрытие всего одно и два способа пронумеровать слои. Но каждому из этих двух способов ему соответствовала одна и та же транспозиция. И вот давайте заметим, сколько у нас получится всего.
Плюс первая перестановки. Может, нужно под модулем, мы считаем внизу фиг минус первая данной перестановки.
Сейчас.
Ну, то есть, как бы...
Да, правильно. Правильно, да.
Фиг минус первая как раз морфизм, нет?
Сейчас.
Если получился набор фиксированности, значит, что все условия.
Сейчас, секунду, давайте это аккуратно место подумаем, здесь чтобы не было путаницы. Сейчас, значит. Нет, вот давайте в том примере посмотрим, да? В том примере, который у нас было одно накрытие, два способа пронумеровать, да? И мы смотрели, чему это соответствовало с точки зрения транспозиции. Это давало одно и то же, одну и ту же транспозицию, да? И там вот это число было единицей. Значит,
Вроде бы написано.
Здесь. Нет, по-моему, все правильно.
Вроде бы все нормально, да.
Теперь утверждение, еще раз, давайте я повторю. Рассматриваем класс эквивалентности накрытий и берем какое-нибудь накрытие из него и берем все способы пронумеровать. Вот. И теперь смотрим, какие получаются наборы транспозиций. И утверждается, что число таких наборов это и есть модуль mu факториал делить на число автоморфизмов.
Ну да, потому что оно не зависит от того, какой представителя мы возьмем в этом классе. Не зависит от... Да.
Ну вот. Okay, so now we see that...
То есть, чтобы получить один в один, нам нужно, с одной стороны, поделить на группу автоморфизмов, потому что для каждого элемента из группы автоморфизмов у нас одно и то же получается. Потому что эти слои мы можем как угодно перенумеровывать, а с другой стороны, там мы можем на геометрической стороне можем любой элемент, ну, в смысле, изоморфные накрытия, они будут отвечать одному и тому же набору перестановок, поэтому на автоморфизм тоже надо поделить. Поэтому мы справа делим на автоморфизм, а слева на μ факториал. Но еще там сверху осталось вот это вот то, что мы уже обсуждали, нумерация лямбд, и ее надо руками добавить там 1 на m факториал.
Yeah, so we have to add by hand this factor, number of automorphisms of mu divided by m factorial, and then there will be perfect coincidence between those two cases.
То есть это уже комбинаторный фактор, который никак с геометрией не связан, просто мы понимаем из других соображений, что мы хотим именно такое определение, и поэтому мы его добавляем.
Yes. So this factor we need to, in order to get nice generating functions which are relevant for topological recursion. And in fact, there are, like I said, like we said, there are multiple ways of defining Puris numbers. And in fact, more classical way to define Puris numbers is without this factor. So if you look at some paper and see there some forest numbers, probably they are without this. So you need to actually check the definition, and you'll probably see that it's like that without this factor. But we need this factor in order to have a nice generating function. Actually, we can plug it into the generating function itself, but from what we'll see in what follows, this will have. All right, so we have finished this part, and we can 10 minutes, I guess. Let me write down the loop equations.
У кого-то включен звук. Полина, возможно, да, спасибо.
So where is, Боря, можешь сделать там линию где-то?
Да. Sorry. So, second. So you want to go to the right, yes?
Yes.
Okay. 1 second. Yeah, we have some huge computations below, but
Наверное, надо будет их уменьшить в размере.
yeah. So okay.
Сегодня какое число? Сегодня 12, да?
Yes. In fact, I had line more to the right. Could you?
Oh, sorry, you already. Sorry, yes.
Yeah. Just.
I have to go further to the right.
Yeah. A bit.
Ну, нам надо потом это все немножко передвинуть, это что-то громоздко.
Mm-hmm.
Okay, so I will give an equivalent reformulation of recursion.
Thanks, Misha.
The reformulation by the loop equations. So where we say that definition a system of symmetric differentials omega gn for g greater or equal than 0 and n greater or equal than 1. Satisfies defined on sigma to the power n, satisfies topological recursion. If it satisfies the following conditions. First, we will have to fix the what's called the unstable cases. So omega 0, 1. Again, we say that omega. Oh, sorry, I'll write it. I guess like okay, omega 0, 1 is y dx. Yeah, sorry, we have let me start with saying that given a spectral curve, sigma x, y, b, b is what will be our omega 0, 2. Then we say that this system satisfies the topological recursion if the unstable cases are what we expect them to be. Omega 0, 2 is b. Then the second condition is the condition of meromorphic. So we say that they should be actually meromorphic. So for all stable GNN, so for all G greater or equal than 0, and for all N greater or equal than 1, such that 2G minus 2 plus N is greater than 0. So what does this condition correspond to? 2G minus 2 plus N is greater than 0 when? In which cases? In which cases 2G minus 2 plus N is greater than 0? Yes, in all cases apart from those two, right? So whenever Gn is not equal to 0, 1 or 0, 2. This is the same. Is it clear? So for all those cases, omega Gn are global meromorphic n differentials on sigma to the power n. So then the next condition is what's called the linear loop equation. Linear loop equation is the following condition, is that for all GNN the following expression, omega G, for all I from 1 to capital M. So we said that X has here, let me mention that in the definition of our spectral curve, X has n simple ramifications. And no other ramifications. So X is only
simple zeros of dx.
Simple zeros of n, which is the same as dx has n simple zeros.
So in case of Hurwitz numbers, it's only 1, 0. So and in case of monotone Hurwitz numbers, it's yes, also only 1. Yes.
Also only 1, yes. So we assume in the flow for topological recursion, we assume that X only has simple critical points, and there are n critical values, right? So n zeros of dx. No, n critical points, yes. and critical points of X. Okay? Critical points, not critical values, but critical points and critical points. So, and simple zeros. In fact, this condition can be listed. We will talk about this probably closer to the end of the course. But this will correspond to some sort of generalization of topological recursion, and there are actually multiple ways to generalize them. Historically, the first way is called the Bouchard-Renard recursion, which generalizes this if you lift this condition that the zeros of the X should be always simple. But it turned out that this Bouchard-Renard recursion does not always behave nicely with respect to taking limits on spectral curves. And there is another definition by Recursion, which is better. It sometimes satisfies, sometimes it coincides with Bouchard-Renard, but sometimes not, and it always behaves nicely with respect to taking limits. But we will probably discuss it if we have time at the end of the course. But for now, we assume that it's simple always. So for all I and so on n, so omega g n plus 1. Let me, if it's n plus 1, then I should write it like that. G n n. Zero, omega g n plus 1 of w z 1 and so on zn plus omega gn plus 1 of sigma I of w z1 and so on zn is holomorphic at w tends to pi. So pi is our I. So for every critical point of X, this thing, you remember what is sigma I, right? Do I have to write down what the definition of sigma I? Sigma I was the deck transformation. So sigma I is the deck transformation near pi such that x of sigma I of z is equal to x of z. So because we discussed this, so our critical points are simple, so near the critical point we have two intersecting sheets, and this sigma I, in the local vicinity, it interchanges those two sheets. Okay? So this is the first condition. It's the linear loop equation. That they are. Though this expression is holomorphic.
Omega goes to pi.
W
goes to pi. Yes.
Yes, it's holomorphic at the point pi. At the point pi, it's a holomorphic expression in terms of W. But also, since they are symmetric, this means that in every argument they are homomorphic, so you can interchange arguments. I guess maybe let's do it. So my suggestion is we are actually 5 minutes late for the break. So my suggestion is to have a break now, and then I will finish this definition at the start of after the break. So first of all, is it clear what is this condition? What does it mean that we require this expression to be holomorphic at this point? Is it clear why is it called equation, for instance? This is a condition that this guy is holomorphic, but why do we call it an equation?
Principal part.
Principal part, yes. So you take a look at the principal part of this expression. So basically all negative terms in the Laurent expansion. Right? So you consider the Laurent expansion of this expression at point pi. This was, recall that this was by our second condition, it was a meromorphic function. So it has a Laurent expansion with some finite number of terms with negative powers, right? And this condition is that the principal part, namely all the terms with negative powers in the Laurent expansion, is 0, right? This is the equation. Is it clear? Is it clear to everyone? And then we have what's called the quadratic loop equation. The quadratic loop equation sorry. In this formulation, if I'm saying that this omega, so it's holomorphic, and additionally, sorry, I forgot to add this, is holomorphic and also should have a simple 0. And has a simple 0. At this point. Now, a quadratic loop equation, it looks very similar to the formula which we have in the original formulation of topological recursion.
In fact, in the seminar, sorry for interrupting, in the seminar list problems, the loop equation defines in terms of not omegas but WGN endpoint functions, but yeah, they are the same. If you look at at practice problem list, and then there are these WGNs, which are in fact the functions corresponding to this and form differentials omegas. Yeah.
Мы, кстати, правильно писали, там dz или dx?
dz.
А 0 откуда берется лишний? Ты можешь проверить, как W с омега были связаны?
Да, по-моему, так. По-моему, я проверил, но я проверю, да.
Так, значит, okay, so the quadratic loop equations, they are, again, for every TNN greater or equal than 0, and for every I from 1 to n, we should have that the following expression, omega g minus 1 n plus 2, w sigma I of w, then z1 and so on zn. So you recall this a term like this from the original definition of topological recursion, right? And then, as you could probably expect, plus sum over g1 plus g2 equals g I degenerate union j equals 1 and so on n. So this sum is just the regular sum, not sum prime, as we had in the original definition. So here, As you can see, let me finish it first. Oh, sorry. So now this expression is very similar to the one we had in those brackets in the original formulation of topological recursion. So what is the difference? What is the difference? The difference is that you do not have this prefactor. Recall the one with in the numerator we have this integral of omega 0 2, and in the denominator we have the difference of omega 0 1, taking out.
What is the equation?
Yes, okay. And the equation is the same as there, basically, is holomorphic at pi and has a double zero. At least a double zero. And here, here we also has at least a simple zero, at least. So the literal equation, this expression should have at least a simple zero, and in the quadratical equation should be holomorphic, and it must have at least a double zero. So this is the equation. So the requirement that this expression is holomorphic and has at least a double zero. So now again, let's talk about a little bit about how it is related to the original formulation of topological recursion. There you have basically the same expression in the brackets, except for this prefactor, like I said. And also there we have some prime. Do you remember? We, in the original formulation of topological recursion, we, in the similar expression, we did not allow in this sum terms where omega 0, 1 appears. But what does it mean if, let's say, this first factor is omega 0, 1? What does the second factor become in that case? It's g and not n, but n plus 1, right? So in this case, if it's omega 0, 1, then it's omega g n plus 1. So we did not want it in the original formulation of the topological recursion because the formula would not be recursive then.
Я не g равно n. И объяснили g равно n. Вы выкидываем один элемент и, а потом еще добавляем.
Почему мы кидаем один элемент?
Сейчас. Ну, 0,1 раз.
0,1 это и пустое. Здесь всегда, кроме z и zg, еще добавлено w, sigma и w. Okay? So it basically corresponds, this term with omega 0, 1, when there is omega 0, 1 there, it corresponded to the left-hand side, basically, of the original topological recursion formula.
Okay, and so I want to add that maybe you add to the definition that it satisfies the topological recursion if and only if, in fact.
No, it's not a theorem. It's another definition. We say that it satisfies topological recursion.
Okay. And also
that this definition is equivalent to the original.
Yeah. Okay. And also there should be the
Right. Yes. There is a fifth condition actually. So the fifth condition is the so-called projection property. I will write it down in one way, but it can be actually, later we will reformulate it a little bit simpler. So projection property. But you see, I mean, the loop equation, it looks somewhat similar to the original formulation, but it's weaker. Because we're only saying something about the principal part. And maybe two further terms, right? It's weaker than the whole topological recursion relation condition which we originally had. So we need to actually add further things. For instance, this projection property, which I will formulate now in one way, but then later we will reformulate it a little bit differently. So for all stable cases, g greater or equal than 0 and greater or equal than 1, such that 2g minus 2 plus n is greater than 0. We should have the following. So omega gn is that 1 and so on that n is equal to sum over I1 In from 1 to capital N.
Maybe formulate it in words now, because if we will not.
No,
Yeah.
I want to write it as a formula like that with the residues, and after that we will talk about this space sigma, but not now. So
Okay, maybe while Peter is writing, I just said that projection property means that there are no other. So these meromorphic functions, which we have, this omega gns, global meromorphic functions, they in fact, so they may have poles. Yes, these meromorphic functions, the rational expressions in symmetric rational expressions in terms of z1, etc., zn, may have the denominator, and this projection property means that that the only poles which omega gn may have are these zeros of dx. So this is the meaning of this projection property, that the in denominator of this omega gns may be only factors of the form z minus some say t, where t is a zero of dx. So these points pi's, yes, yeah, pi. So in the denominator of omegas may only be these the factors of the form z minus pi. This is the meaning of this huge formulas in the fifth in the 0.5. Да, давайте я еще раз повторю по-русски, что действительно вот то, что сейчас страшное выражение написано в 5, это просто такое сложное очень переформулирование того, что в знаменателях этих мероморфных функций омега gn от z1, zn могут быть только выражения вида z минус pi, где pi это вот нули до x.
Смотрите, утверждение в том, что мероморфная функция, она восстанавливается по главным частям своих плюсов однозначно. Вот. И дальше здесь говорит следующее, вот в этом утверждении говорит следующее. Вот посмотрим на омега gn. Да? Вот, давайте отдельно рассмотрим зависимость от W1. Значит, здесь говорит следующее, что давайте возьмем сумму по всем точкам, вот этим вот по их, по всем критическим точкам x, вычетов нашей функции умноженной на вот этот интеграл. Вы помните, что это был за интеграл? Этот интеграл это был что-то типа, ну давайте для сферы как он был устроен. Он был устроен, помните, омега 0,2 для сферы это dz1, dz2 делить на z1 на z2 в квадрате, да? Значит, интеграл устроен как просто единица на, ну вот он тут будет устроен как единица на w минус z, да? Интегрируем мы по, соответственно, вот омега 0,2 от w житого z житого, ну вот интегрируем по переменной, которая отвечает за
Которая не W.
которая не W. W должна остаться, Z.
То есть эта штука не зависит от Z.
Да?
У нас вообще ничего не зависит от Z.
От Z здесь ничего не зависит. Сейчас. Я не правильно сказал.
Какая-то путаница, там слева Z, справа W.
Это W, да, неправильно сказал. W. Z тогда останутся.
То есть можно поставить точку, Z.
Это не поставить точку, потому что W это еще и предел интегрирования.
Да, тут какая-то путаница, там предел интегрирования W житое.
Давайте, да.
В скобках W житое. Сейчас и вправо. И дальше у тебя тоже омега gn от W.
Это все нормально, я потом по W беру вычет.
А где?
Вот здесь.
А скобки как-то расставлены. Со скобками какая-то ерунда.
Нет, все нормально, в том смысле, что здесь вычет я должен брать не от того, что внутри, а от того, что вместе. Как бы вот давайте рассмотрим вот эту штуку как оператор.
Ну, как-то тут неправильная скобочная структура у тебя.
Я правильно скобочную структуру.
Не, ну хорошо, тогда вычет от чего берешь? Ты можешь обвести, от чего ты берешь вычет?
Здесь проблема в том, что у меня есть произведение n штук вычетов. То есть, вот, ну,
Да, ну а дальше, то есть, хорошо, от омеги gn от W1 W1 ты все-таки не берешь вычет.
Вычет и таких вот n штук вычетов. Потом здесь вот эти вот есть интегралы от омега 0,2 и их тоже n штук, интегралы от омега 0,2. И потом уже идет вот это омега gn. И, соответственно, каждый из вычетов, он берется от всего вместе выражения.
Ну вот, да, вот так теперь понятно написано. И теперь можно скобки поставить, наконец.
Ну, скобки здесь стоят в том смысле, что... да. Ну, наверное...
Ну просто так, как написано, невозможно понять.
Это не произведение, на самом деле.
А давай ты распиши, правда, что ты имеешь в виду. Это не произведение, нет, это не произведение. Ну, в смысле, это композиция нескольких вычетов.
Ну, это, если вычет...
А ты можешь написать вот так, как ты снизу написал, только теперь полную формулу.
Хорошо.
Ладно, понятно.
Ну, может, понятно? Ну, вот. Не полная формула, понятно, как соответствует.
Ну, теперь понятно, но не знаю, всем ли.
Надо написать полную формулу, как снизу. Написать полную формулу. Давайте напишем.
И там еще сумма где-то, она тоже где-то в каком месте.
Давайте. У нас не влезет. Ну, на самом деле, еще раз, эта формула выглядит страшно, а смысл у нее простой. Сейчас мы это обсудим. Так слышишь?
Ага. Ну и теперь можно скобки поставить, от чего берется вычет. Вычет берется от всего вот этой... нет, ты сначала хочешь просуммировать еще по E1 и N?
Ну что, в конце можно просуммировать. Каждый из вычетов берется от всего того, что внутри.
Да.
Мне кажется,
Интегралы перемножаются, да?
перемножаются, да.
Да, интегралы перемножаются, а вычеты не перемножаются. Вычеты — это композиция.
But let's recall what was this guy, integral of omega 0 2. Omega 0 2, it was pz1, pz2 over z1 minus z2 squared, right? So what was the integral of that? It was basically 1 over, in this case, 1 over w minus zn minus 1 over pi minus zn, right? So what will happen when you take a residue of something times this guy? So the point is that if you think about this, then basically, this condition it holds for every omega gn which does not have any poles apart from pi's. There are some small subtleties, but essentially it's this condition. We'll discuss it in more detail later. But essentially this condition says that omega should not have any poles at any points apart from pi1 and so on, p1 and so on, pn. This is how you recover a meromorphic function from the information in this poles. Okay. So we'll discuss it later in more detail. But now,
Okay, so maybe let's turn to the problems.
yes. So at this point, we have introduced this definition, and the theorem is that theorem, which we will not prove right now. Theorem. Original definition is equivalent to the Lopez-Weichenk definition.
Okay.
And one small comment is that one can consider a weaker form of topological recursion. Namely, suppose that this last condition does not hold, and you only impose the first four conditions. Then it also what the resulting conditions are interesting, and they correspond to what's called the blobbed topological recursion. So if you have all five conditions, it's the original topological recursion, but if you drop the last condition, you get what's called the blobbed topological recursion, which is also interesting. It's weak. I mean, every topological recursion is a blobbed topological recursion, but not vice versa.
What is block?